In this video, we're going to start to think about how are bonds that we know exist and we know the atomic shapes, but how does that really occur? So let's think about how the orbitals might actually interact. As we start to think about this, we're going to start to consider how do bonds look and what do they look like? So if we were to know that all bonds are created with two electrons, which we do, we tend to think that these two orbitals are going to overlap, meaning they're going to cross paths. But the reality is, if we were to draw a diagram that has the radius here and energy here, which is increasing towards zero here. If we have two atoms and we're asking ourselves, how close or far apart are they? We'll see a graph that looks something like this, where this is the optimum bond length. This is what we see in structures and everything else. If these two atoms are hydrogen, out here we have two hydrogens near but not interacting. And as they go down this slope in this direction, becoming closer and closer together, they start to have far apart interactions. And at this distance, we have a hydrogen-hydrogen double or a single bond. And if you go even further or closer together here, what you start to see in this structure is nuclear repulsion. What I mean is the two atoms can't sit on top of each other in any structure because that's two things cannot occupy the same space. So in this case, we can look at how these orbitals are created and overlapped. And so it's important to note as we think about this that hydrogen has a 1s electron plus the other hydrogen with a 1s electron. And to create this bond, these two atoms are both going to donate their 1s electron to where we can see the two electrons in a 1s orbital. So as these come together, each atom contributed one electron. So when we think about valence bond theory and or VSEPR theory, this states that the interacting energy is stabilized when the two electrons have opposite spins. And we saw that in the previous bond for hydrogen-hydrogen, where the two electrons filled the 1s orbital completely. So a chemical bond is going to be the result of overlap of two orbitals. So if we think about hydrogen-hydrogen, they both have a 1s electron. And so we could draw those as two circles, and then you could draw those as slightly overlapping circles, where this right here is where we'd expect the bond to occur. So what we're going to start thinking about in this video is how does the orientation of the orbitals create the molecular shapes and base geometries that we already know exist. So as we think about this, we're going to start to ask ourselves, how does a tetrahedral molecule exist? And we know it does because we've seen it structurally. So one of the ways that we can start to think about this is to look at the Lewis dot or VSEPR structure for H2S, so hydrogen sulfide. If we have a VSEPR structure, which you can see here on the left, where we have two hydrogens that are roughly 104.5 degrees apart, and we see that because it is base, tetrahedral, and the shape is bent. However, if you were to use different spectroscopy techniques and be able to accurately measure this bond angle, it's actually only 92 degrees. And so this 92 degrees is not at all close to 104.5. So there is some disconnect between the base tetrahedral shape and bend and what we're actually getting. And so the reality is we need to account for this using different mechanisms. And what we're going to start to use is something called hybridization. So hybridization is a mathematical calculation that we will not complete that combines standard orbitals to create hybrid orbitals. And these standard orbitals are often called atomic orbitals or AO. And we're going to create hybrid orbitals. And so we are going to determine the amount of mixing, i.e. how many orbitals mix together and how do they mix together to create each unique base geometry. So the hybridization guidelines are pretty simple. The number of mixed orbitals corresponds to the number of hybrid orbitals created. This first one basically means that if you start with 3 atomic orbitals, you will get 3 hybrid orbitals. And so it's a one-to-one interaction. If 2 things mix together, you will get 2 out. This combination of the orbitals determines the shape of the molecules that we're going to create. And the hybrid orbital created is the lowest energy conformation. So these 3 guidelines or rules are going to tell us about the different shapes that we can see. So the first one we're going to look at is something called sp3 hybridization. And so in the graphic on the right, what you can see is we have 1 s and then 3 p orbitals. So these are not in the n equals 3 shell. It is that there is the px, py, pz. So when you mix these together, what this means is you're going to add these 3 things together. You are going to get 4 identical orbitals. These 4 identical orbitals are 109.5 degrees apart. So in this case, we are going to mix together these 4 orbitals to get 4 hybrid orbitals. So we are going to have 4 atomic orbitals, and that gives us 4 hybrid. So let's look at how this mixing comes together in maybe a little bit more or different detail. So we talked about methane previously, and so we know that carbon has the following geometry or the following electron configuration: 1s, 2s, 2p, with these electron configurations. And so hydrogen still has its friendly 1s. So if we look at the hybridization, or we look at the atomic orbitals first, what we could really make would only be a carbon with 2 hydrogen bonds, because we can make a bond here and we can make a bond here. But there is no way that we could just add an electron into this third, because where would it go? So if we start to think about that, how could we mix these orbitals together in such a way that we could get something else? So I'm going to mix or hybridize these 4 orbitals, and I'm going to get 4 sp3. So sp3, this annotation means s plus p plus p plus p. So when you mix together the sp3, these are still in the n equals 2 shell, so you could write it as 2 sp3. We have 4 electrons that are in this valence orbital shell, and those 4 are going to follow Hund's rules and be distributed like this. And as you add the hydrogen with the single 1s, you could imagine that these will overlap. So you can allow these 4 orbitals to create 4 single energy orbitals at all the same orientation. So one of the ways when people start to look at hybridization is we use the bond angles, but we can also draw orbital overlap. And it looks a little like this, where we start to see these frameworks of different orbital shapes. So this is a very bad, but a wedge line. This back here is your dash. And what you can see is that these overlap. And so we see right here, you would get an orbital overlap that contains 2 electrons. So we see these orbitals in 3D space. So methane is base tetrahedral. It also has a molecular shape of tetrahedral. But let's look at ammonia, which isn't base tetrahedral, or is base tetrahedral, but not the same shape. So we're going to look at nitrogen. We have 1s, 2s, 2p, and nitrogen has 5 valence electrons, which we see this. So if we could, we know that our 1s electron for hydrogen, it seems really simple that we could just add this into these 2p, and that would work. But the reality is that implies that ammonia would have 90-degree angles because px, py, pz are at 90 degrees. And that's not what we see. We see something much closer to 109. So I'm going to hybridize these and get the same sp3 orbitals that we saw with carbon. And in this case, I'm going to distribute my 5 electrons. And this fully filled orbital here is the lone pair. So we can create 3. So if we put our nitrogen in the center, we're going to have this structure. And then one of them, we have our lone pair. And then we have our hydrogens interacting here. And so this lone pair also is in an equivalent orbital. So this shows us how we can create a steric number of 4 geometry because we mix together 4 orbitals. So let's look at sp2 or trigonal planar. So we need a different arrangement. In this case, we are going to mix together 1s and 2p orbitals, again, in any shell. And we're going to get 3 orbitals that if you were to draw this yourself here, you would get 3 identical lobes at slightly 120 degrees apart. But what's really important to remember is that there are in fact 3 p orbitals. And so you have a leftover pure p orbital that is orthogonal, which means 90 degrees to the central axis. So let's look at what that means. So in this case, we're going to look at formaldehyde, which has a Lewis dot structure that looks like this. And so we know that it has a geometry of tetrahedral. But let's look again at the carbon electron configuration. And it looks like this. And so we only need to create 3 hybrid orbitals. So we are going to mix together these 3 here. So you just need to mix the ones that you're going to use. And this gives us sp2. This 2 means that you only added 2 p orbitals to your s orbital, as opposed to the 3 in the sp3 hybridization. And then we have 1 p orbital left over. So these are all quite similar in energy, so we distribute our electrons like this. So what we're going to see is that this leftover p orbital is going to be above the internuclear axis. So when we think about how this is going to look, we're going to have our carbon with its 3 lobes. We have our hydrogens out here. And so it's going to interact with an oxygen that has this orientation. And so this oxygen is going to be able to create a single bond here. But we have this double bond. And so this pure P here is going to be part of a double bond. And that double bond is going to be above and below the internuclear axis, which means that it's right here. So you can think of it as kind of making a sandwich. And so what's really happening is that this double bond is going to be called a pi bond. We're going to start to refer as the internuclear bond as a sigma bond. And so it's important to note that the oxygen has a different orientation. So oxygen has not been hybridized. So in this case, for oxygen, it has the 2s, 2p, And so one of these p orbitals here creates the sigma bond, and this other one is going to be involved in the pi bond. And so the other two are lone pairs, and the orientation of those is somewhat complicated and left out because it is not our central atom. So let's look a little bit more in depth what sigma and pi means. So an internuclear bond, so a regular bond, is a sigma bond. So all sigma bonds are single bonds. When we start to think about double and triple bonds, these are going to be composed of one sigma and one pi, or one sigma and two pi. So if we were to think about an interaction between two lobes, where we have an atom here, regardless of what its hybridization is, this is a sigma bond. It's along the internuclear axis. The pi bonds can be above and below, and they could be here. You could also see them at 90 degrees to that, basically in and out directly along this bond. But a pi bond or a triple bond, which is two pi bonds, is not involved in the nucleus or along the nuclear axis. So one of the things that pi bonds are really useful for is thinking about rotation. So we don't tend to think about rotation a lot, but if we were to have this structure, so carbon, carbon, if we have this structure or this structure, one of the things that is different about these two is they're missing two hydrogen atoms. But when we start to think about the one on the left, we could draw this and it would look something like this. So we could put any of our atoms, as long as each carbon has two hydrogens and a chlorine, in any arrangement. And I'm going to leave off the lone pairs for just a second, although I'll come back and fill those in. So when we look at this, we can see a free rotation around this bond. But in the structure on the left, we actually have a p orbital, this pure p orbital left over in both carbons, and it's going to be right here. So this molecule cannot rotate, so the arrangement is trapped. And so one of the things that pi bonds do is they prevent rotation. So if you look at the structure on the left, that base tetrahedral can kind of spin like a propeller. Once you add in a pi bond or a double or a triple bond, you're going to lose that rotation. And so this is one of the things that pi bonds or double bonds or triple bonds are really known for. So one of the next types of hybridizations is we want to create a linear molecule. And so these are going to require hybridization of just two orbitals, the s and the p. So we're only going to mix together two. We're going to have two leftover p orbitals that will be orthogonal, meaning at 90 degrees, one above and below, and one in front and behind. So we can look at ethylene, which is this CH. And so we can create for this carbon or the other carbon, we'll have our 1s, our 2s, 2p orbitals with the usual valence electrons. In this case, we are just going to mix together two of these and get two sp orbitals and two pure p orbitals. And those 4 electrons will be distributed among them. So this is going to allow us to create a bond with the hydrogen, and this one will bond with the other carbon. This and this will be our above and below. So if we draw this out, our two carbon-carbon bonds are going to look like this with our hydrogens on the end. So we have a sigma bond here, a sigma bond here, and a sigma bond here. So once we start to think about the leftover p orbitals, if the sigma bond is in the plane of the paper, we're going to have one that is going to be up here. We'll have one, and I'm actually going to use a highlighter. We'll use it green just to kind of make our lives a little bit easier. And it's going to basically point out in front of this to where we have a set of two different bonds. So in this case, the molecule still can't spin, but it's going to be trapped in this arrangement. And so we can see that this is created from one s and one p orbital, and there are two leftover p orbitals. So we can also create sp3d and sp3d2 hybridization. And so in this case, what we see is that for the sp3d, we've added our one s, our three p's, and a single d orbital together to give us 5 sp3d hybrid orbitals. And this is trigonal bipyramidal. And so when we think about this hybridization, this will be for larger molecules in that case. We can also see a similar hybridization for the octahedral. But in order to create a steric number of 6, we need to combine 6 orbitals. And those 6 orbitals are an s, 3 p's, and 2 d's, which gives you a total of 6. And that gives you 6 identical sp3d2 hybrid orbitals. So these are all of the different types of hybridization. So if we look at this, we have 5 base geometries, which have steric numbers 2 through 6. So one of the things we want to notice is that the steric number and the number of orbitals hybridized and orbitals created are all the same number. So we can remember the hybridization of any atom based on its steric number. So in this case, we know that you start with an s, and then you're going to add in a p orbital, and then you'll add in 2 p orbitals, then 3. Then you'll add 3p and a d, 3p and 2d. So the greatest amount of hybridization is for an octahedral molecule, and you'll get this. So let's look at some examples. So we want to draw the base and molecular shape. So in this case, we want to draw a Vesper structure showing lone pairs, formal charge, and ask the question, what is the hybridization of the central atom? So for bromine, we're going to have 7 plus 3 times 7. That gives us 28. So we'll have bromine in the center. We're going to add our 3 fluorines. So in this case, we have used 8 plus 8 plus 8, which is 24. So there are 2 leftovers. So our geometry structure is going to look somewhat similar to the Lewis dot structure, except we will have the lone pair electrons on the bromine. So then we need to ask ourselves, we have this base trigonal bipyramidal. And the shape is also T-shaped. And so we ask ourselves, what is the hybridization of bromine? So bromine has a steric number of 5, which means that we have to have 5 things that hybridize. So the hybridization is going to be sp3d. And we know that because in this case, it took 5 orbitals to create a steric number of 5. So let's look at HCN. So the valence electron is 1 plus 4 plus 5. We're going to connect these together, and then we'll go ahead and give octet to nitrogen. So 2, 4, 6, 8, 10. We've used all of ours, but carbon doesn't have an octet. So we're going to go ahead and remove these 2 and go ahead and draw a structure like this where everyone has octet and everyone has a formal charge of 0. So it turns out that both the Lewis dot structure and the Vesper structure, so we have linear base and a molecular shape of linear. And so this carbon here has a steric number of 2, which means that the hybridization here is just sp because it only has 2. So let's look at AlCl3. So aluminum has 3 valence electrons plus 3 times 7. That's going to give us 24. I'm going to slide this up for a little more space. So aluminum is connected to 3 chlorines. We'll go ahead and give them octet as we put them out. So this is octet. Everyone has octet except for aluminum, but aluminum is allowed to have less than octet because of where it lives in the periodic table, because its formal charge is 0. So the VSEPR structure is going to have each chlorine at 120 degrees from one another. So this is trigonal planar. Trigonal planar. And for aluminum, it is going to have a steric number of 3, so it is just sp2 hybridized. So last, we're going to slide back over here to look at xenon tetrafluoride. So we have 8 plus 4 times 7. So that's 28 plus 8 gives me 36. Put our xenon here in the center. Give it 4 fluorines. Go ahead and use up electrons by giving it octet. So we've used 32 of 36, which tells us there are 2 left over, which gives us a steric number of 6, which tells us it's base octahedral. So we can put the xenon in the center. We're going to connect all of our bonds like this. We're going to put the 4 fluorines along the central axis in the equatorial position, because that allows the lone pairs to be as far apart as possible. And so in this case, the base geometry is octahedral. The molecular shape is square planar. And with a steric number of 6, we have to combine 6 orbitals, which gives you sp3d2. So in order to identify the hybridization, it corresponds to the steric number. So let's look at another slightly different example. So this is the structure for vitamin A, and it's asking us to do 5 things. What are the number of sigma bonds? What are the number of pi bonds? What is the hybridization of 3 different atoms? So in this case, I'm going to start from the bottom. So the hybridization for the green atom, which we see here, it has a steric number of 1, 2, 3, 4, which means that it has to be sp3. It's also tetrahedral. So when we look at the one with the diamond, we see 1, 2, 3 things connected, which makes it trigonal planar, which also means that it has to just be sp2. For the red one, we see 2 bonds and 2 sets of lone pairs, which gives us a steric number of 4. From here, we have to remember that the lone pairs are hybridized. And so in this case, this oxygen still has an sp3 hybridized orbital, even though it doesn't have a full tetrahedral structure. So to determine the number of sigma bonds and pi bonds, we just count. So I'm going to get out a highlighter, and then I'm going to highlight every single sigma bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 35, 36, 37, 38, 39, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 51. So I get 51, and then we'll use a different color highlighter. We'll use red to calculate all of my pi bonds, so you're just looking for the double bonds. So we have 1, 2, 3, 4, 5. And that means that there are 5 pi bonds. So we can now look at any large atom and start to think about how this atom or how this molecule comes together and what hybridization leads to that.